All right, Honors Chem people, we are going to just go back a little bit. We got cut off when we were talking about the ammonium ion. When we got cut off, we were looking at the amount of electrons. Because we have a positive charge here, we're going to subtract one electron. So that gives us a total of 8 valence electrons. So we put nitrogen in the middle and put a single bond to each of the hydrogens. Now, because we have the full octet satisfied for both hydrogen and nitrogen using the 8 electrons, we know that we're done in terms of just the Lewis structure. But because it's an ion, we put these brackets around here and we put the charge up on the upper right-hand corner to show that it's an ion and to also show what charge it has. Now, because we have 4 bonds coming out of that center atom, we know that we have a tetrahedral shape. We know the bond angle is 109.5. Because we have that charged particle, it's going to be polar because it has a charge. Anything that is ionic is going to be polar just because it's charged. Okay? So, on to our next thing. We now need to start talking about double and triple bonds and what that does with the electron arrangement. Okay, so here we go. We're going to go through these bond angles really quick. So multiple bonds, and we also have something called resonance structures. Now, resonance structures are something where we have a bond and a half going on. Now, Lewis structures don't really let us draw a bond and a half, so we draw what's called a resonance structure, and I'll get into that in a minute so that you'll have an idea what's going on here. So we want to draw the Lewis structure for oxygen gas, and the oxygen gas is a diatomic molecule, so it comes to us in groups of 2. So we do get O2. So let's look at oxygen on our periodic table here. So if I look at our periodic table and I look at oxygen, I am in group 16. So that means that I have 6 valence electrons for each of those oxygen atoms. So oxygen gives me 6 valence electrons, and I've got 2 of those oxygens, so I have a total of 12 valence electrons. Now, because I only have 2 atoms, I don't really have to think of a center atom because the no atom is going to be in the center here. So we're going to do oxygen. Now, remember, this bond gives me 2 electrons. I want to have an octet. So in order to have an octet on each of these oxygens, I'm going to have 3 lone pairs or 6 electrons that are not bonded. So let me put in these lone pairs. 3 lone pairs on each of those oxygens. That will satisfy the octet, but let's now check how many electrons I have used. So let's count them up. I've got 2, 4, 6, 8, 10, 12, 14. I've used 14 electrons. I only had 12 to use. So the question then becomes, how do I satisfy the octet rule for the oxygen and only use 12 electrons? What I'm going to need to do now is I'm going to need to throw in a double bond. If I have a double bond, I will use fewer electrons while still satisfying the octet. So let's give it a try. So I'm going to have oxygen here, and I'm now going to double bond it. This means I don't have 2 electrons going back and forth being shared, but now I have 4 electrons going back and forth and being shared between the 2 atoms. So that means each oxygen here has access to 4 electrons. So they only need 4 more each to satisfy the octet. So that would give me 2 lone pairs or 4 electrons on each of these oxygen atoms that I would need to do to satisfy the octet. Now I have satisfied the octets here. I have 2, 4, 6, 8 electrons on each oxygen. So let's count total. I've got 2, 4, 6, 8, 10, 12 electrons, which is what I actually can use. So this oxygen double bound to the other oxygen is indeed what we would find for elemental oxygen in our air. Now, the only thing I can do shape-wise between two atoms is a line, right? So it's going to be linear. Now, the question is this going to be polar? Now, both of these atoms are the exact same electronegativity. So they're both going to have the exact same pull on those electrons. So if they're going to have the exact same pull on those electrons, this would be a non-polar molecule. Okay, let's do carbon dioxide. Okay, now carbon dioxide is CO2. What's going to be the center atom? Carbon. Hopefully you said carbon. Okay, so let's count up our electrons. So carbon has 4 valence electrons. This should be second nature, hopefully by now. Oxygen, let's just do it on the periodic table just to give you a hint. So there's carbon, so it's going to be 4. Oxygen has 6, and we've got 2 oxygens. So oxygen has 6 valence electrons, and we've got 2 of them. So 4 plus 12 gives us a grand total of 16. Okay, so we're going to try this. So we're going to put carbon in the middle. Now, each of those dashes are 2 electrons. So the oxygens have access to 2 electrons. So they're going to need 3 lone pairs to satisfy their octets. And carbon has access to 2 electrons here and 2 electrons here. So 4, it needs 4 more to satisfy its octet. Okay, so everyone's octets are satisfied. Let's look and see how many electrons I used. I used 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. I used 4 more electrons than I have. So that's not going to be it. I should probably, let's try a double bond on one side. So this oxygen on the left already has access to 4 electrons. So we're going to need 2 lone pairs here. This oxygen on the right has access to 2 electrons. So we're going to need 3 lone pairs here. Okay. And then carbon has access to 6 electrons. So it's going to need 1 lone pair. Let's count how many electrons I have used. I've used 2, 4, 6, 8, 10, 12, 14, 16, 18. Still too many. That's not going to work. So maybe throw in a double bond on the other side as well. So let's do this over here. Okay, let's look at the oxygens first. The oxygens have access to 4 electrons. So they need 4 more to fill their octet. So I'm going to put in 2 lone pairs on both of the oxygens. Now to look at carbon, it has access to 2, 4, 6, 8 electrons already. It is full. That's all it can do. So let's count the electrons that we have used and verify that we are still within our rights. So we've got 2 here, 4, 6, 8, 10, 12, 14, and 16. We are good. So our Lewis structure for carbon dioxide is this. Now, the trick about finding shape with double bonds count as one area.
If you're in the building, would you please have attention 5160? Rich White, please dial 5160.
Double bonds count as one area of electron density. So we have 4 bonds on that central atom, but because we have double bonds, this is going to be one area, and this is going to be one area. They overlap each other physically. So this carbon really has 2 areas of electron density around that center atom. So when we look at our chart back up here, for 2 areas around that center atom, in terms of shape, is it going to let me scroll? 2 areas around that center atom gives me a linear geometry and a bond angle of 180. Okay, remember double and triple bonds count as one area. So our shape here is going to be linear. Okay, now do we have electronegativity that is different between oxygen and carbon? You betcha. Carbon is about 2.5 and oxygen is about 3.5. So it's fairly electronegative towards the oxygens. But because these are both 180 degrees apart from each other, they're pulling the opposite directions. So they cancel each other out. So because they cancel each other out, this is going to end up being nonpolar. Okay? And we end up with a bond angle of 180. Okay? Let's do the Lewis structure for sulfur dioxide. So sulfur dioxide, SO2, sulfur has 6 valence electrons and oxygen also has 6. So sulfur has 6, oxygen has 6, and we've got 2 of them because it's sulfur dioxide, right? That gives us a total of 18 valence electrons that we've got to place. Now the question becomes, what's in the middle? Hopefully you said sulfur. Sulfur is the least electronegativity. So let's do this. So if I do sulfur and oxygen, the oxygens need 3 more lone pairs to satisfy their octet, to have 8 valence electrons. And sulfur already has access to 4 electrons, so it needs 4 more to satisfy its octet. Now the question is, how many electrons have we used? So let's count them up. I've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I only have 18 to use. So because I only have 18 to use, I need to put in a double bond. Now, does it really matter what side I put the double bond at? No, it doesn't. So the single bonded oxygen that I drew here on the left is going to need 3 lone pairs to satisfy its octet. The double bonded oxygen that I drew here on the right is going to need 2 lone pairs to satisfy its octet. Now let's look at sulfur. Sulfur has 3 bonds to it, so it has access to 6 electrons, which means it still needs a lone pair to satisfy its octet. Now, if we count up our electrons, we've used 2, 4, 6, 8, 10, 12, 14, 16, 18, which is indeed the case. Now, so we would have this be our Lewis structure, but we have a slight problem with this. So let's go in with this problem. A double bond between 2 atoms is always a little bit shorter than a single bond between the same 2 atoms because we have more electrons crunched in there, so we are actually attracting the nuclei closer and closer with those electrons in between. Okay? So what would we expect to see with an SO2 molecule? Would we have one side of the SO2 that's got a long bond and the other one short? That's what we would expect to see looking at this Lewis structure. But actual experiments have shown that the bonds are equal length. So in reality, We don't have one single bond that is nice and long and stretched out and one double bond that's kind of short. We actually have 2 1.5 bonds. So in order to show that in Lewis structures, what we do is we write what is called a resonance structure. So what we will show with sulfur dioxide is we will write that sulfur dioxide actually resonates or is in between these 2 drawings. And the reality is somewhere in the middle. And so this is a resonance structure where we have it resonating between the 2. And we bracket the resonance structures. We can either bracket all of them together or single resonance structures with arrows going back and forth between the 2. Now, the thing that we need to look at to determine the shape is we need to find the number of electron dense areas around that center atom. So let's use this bottom resonance structure. We have 1, 2, 3 areas of electron density around that resonance structure. 2 of the areas are bonding, 1 is not. So let's look at our chart. I'm going to look at this chart. I think this chart is a little bit better. So if I have 3 areas that are electron dense, where I have 1 lone pair, I will get a bent geometry. Okay? So my shape here is bent. Do I have electronegativity differences? Let me draw it the way it really is shaped. Do I have electronegativity differences between sulfur and oxygen? Oh yeah, sulfur is not nearly as electronegative as oxygen is. So I will have a dipole this way and I will have a dipole that way. So overall, we will have, if we add that all together, we have a dipole going like this. So yes, this molecule will be polar. And the bond angle, remember we started with a trigonal planar. So trigonal planar has a normal bond angle of 120. But remember, these lone pairs take up a little bit extra space and they smush the other bonds down. So when we're all said and done, we're going to have a bond angle of about 117.3. Okay? So these 2 structures are equally correct for sulfur dioxide. They are called resonance structures. Okay? Let's do carbonate. Now, the carbonate ion, we haven't done carbonate yet in terms of ions, is CO3 negative 2. Now, remember, when we have charges, if it's a negative charge, we add that many electrons. If it's a positive charge, we subtract that many electrons. So since we have a charge of negative 2, we are going to add 2 extra electrons. Okay? So carbon, we have 4 valence electrons. Oxygen, we have 6 valence electrons, and we've got 3 of them, and we've got the 2 extra electrons from the ionic charge. So 6 times 3 is 18, plus 4 is 22, plus 2 more is 24. Okay, so let's see here. I've got carbon, and if I draw a single bond to each of the oxygens have access to 2 electrons. So if I draw 3 lone pairs on each of these oxygens, I will satisfy their octets. And carbon has access to 1, 2, 3 bonds, so that gives us 6 electrons. So carbon's going to need a lone pair here. And because it's an ion, we are going to bracket it and we are going to put the charge. Okay, so I satisfied the octets. Now let's check how many electrons I've used. Okay, so I have used 2, 4, 6, 8. There's another 8, so that's 16 plus another 8 here. That's 24, and 2 more here. So I've used two electrons too many. So I need to throw in a double bond. You're right. Now, I'm going to do this over here because I'm running out of room. So that means one of these oxygens is going to be double bonded, which will mean it needs 2 lone pairs. So 2, 4, 6, 8 electrons to satisfy that oxygen. This oxygen will have 3 lone pairs to satisfy its octet. So 2, 4, 6, 8. And this will also need 3 lone pairs to satisfy its octet. Now for carbon, we have 1, 2, 3, 4 bonds. So that satisfies its octet. We are going to put a bracket and put the charge. Now we have used 2 fewer electrons. So I've got 2, 4, 6, 8 oxygen electrons, another 8 here, and another 8 here. So I have used my 24. But just like the sulfur dioxide, when we look at the carbonate ion, one of the bonds is not shorter than the other. So in reality, this double bond is kind of shared between all of the bonds. So we really have like a 1 and a 1/3 bond going on. So we need to show resonance. So we need to show that the carbon, the double bond could be down here on this oxygen, or it could be over here on this oxygen. All 3 of these drawings are equally valid. And we have resonance between all 3 of these because in reality, the reality is a blended model of all 3. We really have 1 1/3 bonds going on here. So let's look at the shape and the bond angle here. So the areas of electron density that we have around that center carbon, we have 1, 2, 3. So if I look at my chart for 3 areas of electron density, okay, if I have 3 areas of electron density and they are all bonding, I will have a trigonal planar geometry with 120-degree bond angle. Okay, it should remind you of an equilateral triangle, right? Equilateral triangle. That's what we're doing here. Okay. Is it gonna let me scroll? No, it doesn't want to let me scroll. Oh my. Okay. So when we look at carbon dioxide, or not carbon dioxide, but carbonate, we will have the bond angle of 120, and we will have, is it going to let me scroll to where I actually want to be now? Yeah. Okay, so our shape here, let's get rid of that. Our shape here was trigonal planar. And our polarity, we have a charge anything that has a charge is going to be polar. And our bond angle is 120 degrees. Okay, let's look at nitrogen gas. Now, nitrogen gas is N2. It is diatomic, just like oxygen. And if we look at nitrogen, nitrogen gives us 5 valence electrons. So if we have 2 nitrogens, that gives us 10 valence electrons. Okay, so here we go. If I share a single bond, that means each of these nitrogens has access to 2 electrons, which means that I need 3 lone pairs to satisfy their octet. So let's put in 3 lone pairs to satisfy their octets. Okay, so I've satisfied the octets. Let's see how many electrons I've used now. So let's change the color. Let's count up the electrons. I've used 2, 4, 6, 8, 10, 12, 14. I have used 4 more electrons than I really can. Now, hopefully by now you've realized that each double bond saves you 2 electrons. I need to save 4 electrons. So in order to save 4 electrons, not only do I need a double bond, I actually need a triple bond because I need to save 4 electrons, not just 2. So let's put in that double bond. Well, actually, let's just go straight to the triple bond. Oh, come on. Please be responsive. Triple bond. So if I have a triple bond, that means these 2 nitrogens are sharing 6 electrons. 2, 4, 6 electrons. So in reality, to satisfy their octet, they just need a lone pair on each of them. Okay, so when I do this, I have used 2, 4, 6, 8, 10 electrons. So I have used the proper amount of electrons. I've satisfied the octet for the nitrogen. So remember, the only thing I can do between 2 atoms is align linear. And because nitrogens are equal in terms of their electronegativity, the equal pull of the electrons is going to make them nonpolar. Okay, let's do cyanide here. This is hydrogen cyanide, and they used to use it way back in the day as rat poison. Cyanides have always been used as poisons. So, first thing to do is to count up the valence electrons. So hydrogen gives me 1, carbon gives me 4, nitrogen gives me 5. So I have 10 valence electrons. Are you thinking what I'm thinking? We had the same thing up here. So are we going to be needing to throw in a triple bond somewhere? Okay, the next thing to do is figure out what's going to be in the middle. So what's going to be in the middle, carbon or nitrogen? Which one's more electronegative? Which one's the least? Carbon's the least, so we're going to put carbon in the middle, okay? So here we go. Carbon in the middle, bonded to nitrogen. Now remember, hydrogen can only have 2 electrons, and it already has the 2 electrons with the bond with carbon, so it's done. Nitrogen, on the other hand, can have 8. It has 2 with the bond with carbon, so let's put in 3 lone pairs to satisfy that octet. Now carbon in the middle has access to 4 electrons, so it needs 4 more to satisfy its octet. Now let's count up our electrons that we have used. We have used 2, 4, 6, 8, 10, 12, 14. We have used 4 more than we actually have. We only have 10. So remember what we had to do to save 4 electrons? We had to put in a triple bond, either 2 double bonds or 1 triple bond. I can't put in a double bond here because hydrogen can't do any more than 1 bond. So the only other option I have is to put in a triple bond. So I'm going to put in a triple bond between carbon and nitrogen. So the hydrogen's satisfied. The nitrogen has 2, 4, 6 electrons already, so it needs a lone pair. Carbon already has 4 bonds on it, so it has access to 8 electrons, so it is done. So let's count how many electrons I have used. I have used 2, 4, 6, 8, 10 electrons. So I am done. This is the structure. So hydrogen, single bond to the carbon, and then carbon triple bond to the nitrogen. Now, the thing to determine is how many areas of electron density do I have and the polarity. So remember, single, double, and triple bonds are all counted as one area of electron density. So in reality, I only have 2 areas of electron density around that center carbon. And because I have 2 areas of electron density, the shape that I'm going to have is linear. So that gives me a bond angle of 180 degrees. Now polarity. Carbon is more electronegative than hydrogen, and nitrogen is yet more electronegative than carbon. So we are going to have an overall pole going like this, where we have a partial positive on the hydrogen end and a partial negative on the nitrogen end. So this will be a polar molecule. Okay? All right, that is it for today. We are going to go into naming next time. So from here on out, it's going to be review. Have a great day. Talk to you later. Bye.